35, so I have a bit more time afterwards. The bus will leave a bit later, I guess. Or so we are in the, I want to prove this slightly more general theorem. Well, more general theorem with rules in n dimensions, and all I need about G mod gamma is that it's compact, meaning the injectivity radius is uniform. It's sort of the gamma only enters the picture when I look at 2 points that are further away. We will see where it enters. Now, then I have this finite volume that are normalized to be 1, and I'm assuming it's compact. And I have this element, this R diagonalizable. I'm thinking of something like this, for which I need that the action of A on the quotient is mixing. That's the only ingredient for the argument that I will use. So you can forget all about the assumptions as long as you're happy to assume that the action of A on that quotient is mixing. Then the conclusion is that this group acts uniquely ergodic. So how are we going to prove that? We need somehow some averaging gadget, some ergodic sums, ergodic averages, right? But for this group that I define like this, so how do I find such, technical term is Fellner sets, how do I find such Fellner sets? Well, take the one ball inside G minus around the identity. That's the metric one ball inside this group. And then I use that to define bigger sets. What do I have? I have that conjugation normalizes this group. And you should think of some group like that. It's a closed subgroup if we think of a linear group. Then this is automatically a closed subgroup defined by some entries being 0 and some entries being 1, and then some entries have no constraints. So do a calculation for this A, calculate what that group is, and you will see this picture like star star. And the element that I use to define the group, of course, normalizes the group, so I can define bigger and bigger sets by conjugating my one ball by powers of A. But I need to be careful which direction I'm conjugating, because if I'm conjugating the way one normally would, then I make this set smaller and smaller and smaller, which I don't want to do because I want to use the sets for averaging, so I should conjugate in the other direction. And then these sets increase to the whole group Ga minus. And you can check that these sets are Fellner sets where you're allowed to assume that the boundary of that ball has measure 0, because if it doesn't have measure 0, then just change the radius so that it's true. So these things, this set here, it's a sequence of sets which has the property that if you shift that sequence a bit, a fixed amount, then the symmetric difference in relationship to the original set gets smaller and smaller and smaller. That's the property of a Fellner set. So M of Bn, symmetric difference Bn G divided by M of Bn goes to 0 as n goes to infinity for G inside the group Ga minus, and the M is the Ga minus M. So this group that we're talking about has a Haar measure, and it actually is a quite easy Haar measure. So for instance here it would be just a back measure. In general this Ga minus might be a nilpotent group, something like a Heisenberg group, and then it would be the Lebesgue measure. So these groups are nilpotent. They're somehow easier, you should think, in some sense, than the group that we started with, which might be simple. Okay, so the aim, and that's the equidistribution game, and it's of course equivalent to the unique ergodicity game. The game is that when I'm integrating at a given point along the orbit, and I go up to Bn, and I integrate with respect to the H measure. Luckily, this group is unimodular, so I don't have to tell you whether it's left or right H measure. And then I divide by the measure of the set over which I'm integrating. So that's the ergodic average. For the point x, the group action Gm minus, and the current quotation mark interval Bn. That's the perfect analog of the ergodic average that we have seen yesterday. And you can prove ergodic theorems for such actions, for such Fermat sets, etc. Elon will be here tomorrow. You can ask him about that in the most general context. But we don't need that. We will prove that directly without any ergodic theorem, only using mixing. And what we will prove is that this converges to integral over capital X dm capital X, where the H measure on capital X is normalized to be a probability measure. Then it makes sense, because on the left you have a probability measure, on the right you have a probability measure, so there's some chance this is true. That's what we prove. For which f all continuous functions. As n goes to infinity, for all f in C of x.
Strictly speaking, to deduce the statement of the theorem, you do need the ergodic theorem.
No. Because, yeah, but mean would be sufficient. Mean is very easy. Mean, yeah, would need the mean ergodic theorem, but mean ergodic theorem is easy. And then I can conclude that the unknown invariant measure would have to be m of x. I agree. But if it's really R2 which is acting, then the ergodic theorem is easy anyhow, and much older than the work of Elon. Okay. Now, what's the problem really, in some sense? The problem is, let's think of the horocycle flow. Maybe our A is really the geodesic flow, and the Gm minus is really the horocycle flow that we've defined before. Then this would be a one-dimensional integral, and this is a three-dimensional integral. So this difference of one-dimension and three-dimension, that's the issue, right? So it would be good to have something two-dimensional as well, so that we can make this a three-dimensional. Maybe it would be better to have this being a three-dimensional integral. So we need two more dimensions to make the picture bigger. And this is the group PA plus, say, parabolic, and somehow opposite to the minus that I had before. So this is the element of the group of all elements G in G, for which I conjugate, but this time I have to conjugate as n goes to minus infinity. If I conjugate in the same direction my element as before, then my n should at least go in the other direction so that it corresponds to the other thing. And I don't want this to go to the identity. Why not? Because then I would get a one-dimensional group again in the horocycle case, which isn't two. I want two dimensions. So instead of that, I say space-bounded. That's now a two-dimensional group in the case of the horocycle flow, because it would be the opposite horocycle and the geodesic direction. And let V in PA plus be a small neighborhood of that entity in PA plus. How small? We will see. Well, let's see it now. How small? Fix some f in C of x. If you have a continuous function on a compact space, it's uniformly continuous. So fix some epsilon greater than 0 and choose delta greater than 0 as in uniform continuity. And then choose V such that the wrong conjugation, a to the n, g, a to the minus n, distance of that to the identity is less than delta for every n lesser or equal than 0 and for every g in this neighborhood V. That's the small enough. So the small enough depends on the function and the epsilon that I've chosen. And why is this possible? Well, because of every complete case, you will see that this is quite true. And if you want to prove it in general that this is possible, just linearize the picture, go to the Lie algebra by taking the locally defined logarithm, and then you just have a linear map which corresponds to this conjugation, and you have a vector whose orbit stays bounded. Well, if your vector has a bounded orbit under a particular linear map, then it can't go up and then go down again in an arbitrary up fashion somehow. These vectors that stay bounded, they don't increase in size by an unbounded amount of size. So you can choose the V such that this is true. Just by linearizing and going to the Lie algebra, then it all works. You may ask me about this step later. Let me, in our case that we talked about before, let me tell you what the PA plus is. My A was e to the 2, e to the minus 1, e to the minus 1. The GA minus was this thing. And the PA plus would then be star, 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 0, 0. And if you conjugate that in the wrong direction by A, meaning n less or equal than 0, you will explode those zeros, but they are zeros, so they are not exploding. You will not change this, and you will make these things smaller, so it's very easy to achieve all of that. Okay? Now, I was saying I would like to have a three-dimensional integral. This is one-dimensional, and I would like to have a three-dimensional one. So I will invoke the V here to make this one-dimensional integral three-dimensional. So let me call this A, N, F. So that I have a name for it. That's the nth average for the function f. And now let me write down something. I need a bit more space. Of course, 1 over m GA minus Pn m PA plus V. So No. Let me use positive ends all the time, not negative ends. So I'm conjugating the set V by e to the minus n. Then this stays delta small. That's my assumption on the set V. Right. And now I'm integrating twice. Once over the set Bn and once over the set A to the minus n V a to the n. And I'm integrating f, x, u, and now a to the minus n V a to the n. And let's say V is this thing here. And maybe, strictly speaking, I shouldn't have it here. This is the element that I'm integrating over. Never mind the notation. Okay. It's again a probability measure that I'm integrating over on this side, right? Because I normalized by the extra integration that I have. But what do I know about this? I know that this is delta close to the identity, which means that this, the whole element here, is delta close to that element. Which means that the value of the function is epsilon close to the value of this function. So I have amplified the integral in the sense that I made it a higher dimensional integral, but I haven't changed the average, at least not significantly. I've only changed it by an epsilon. Because of the uniform continuity and my choice of the set V. So I will forget about the original definition of the average and keep working with this more complicated expression, which now is correct in dimension. This is now, in the case of the whole cycle flow, a three-dimensional integral. Complicated looking, but three-dimensional. I will write it down one more time here, so that we see clearly what's going on. And then we work with it further. So the average that we're interested in is epsilon goes to 1 over mg b mg a minus bn m p a plus v of a to the minus n a to the n integral bn a to the minus n v a to the minus a to the n f of x u the u itself, the set bn itself, also had a definition in terms of this conjugation here. So maybe to make it even more complicated, let me put the definition of bn more or less into this formula also. So then I have a to the minus n b1 a to the n, my domain of integration, and the u I now write as a u inside the, so the u is now secretly in b1, and the V is in the V. I'm just playing with symbols. Okay. This is what we have, right? Now let me erase everything that I have more space. We will soon start to make it easier looking, right? If this is the sort of the top of the hill, now it will become easier. In formula.
Do you need to normalize by the conjugated at the end as well?
Yeah, every group that I write down is normalized by A.
Yeah, that's one that's normal, so one like that.
It's fine. It's fine. It depends on how you interpret this strange looking expression, but let's agree to interpret it correctly so that it agrees with what we had before. Now, what I really would like to have is not an integral over two groups, I would like to have an integral over one group. Right, I would like to have an integral over the measure on G, not measure on G minus, measure on PA plus. And there's a nice little lemma that says there is some compatibility between the H measures. Suppose G is a nice group and H and L are closed subgroups such that number one, H intersection L should be the trivial element. Our subgroup G minus and the group P plus, they satisfy that. If you, in one direction are isototic to the identity and in the other direction you stay bounded, then somehow you have stayed bounded even before that time, which means you actually equal to the identity. If you think it sort of back and forth, you realize that it has to have been the identity all along. Or you can also look at the pictures, how I, in my case that I draw, I define the PA plus by something vanishes and the G minus by something else vanishes, and actually everything has to vanish if you're in both groups, except at the places where you have to be equal to 1 because you're close to the identity. Okay. So this is very easy to check in our case. And then I want that HL has positive H measure Yeah, people are still very quiet, so nobody asks me which H measure, right, left, right, and so on. So I need to have a bit more assumptions, and then maybe clarify some of the statements over there, because I didn't say which H measures, except for one of the groups I told you that it's unimodular, and that's great, because then I don't have to tell you which H measures, it doesn't matter. But actually the other group is not unimodular. So I should have told you which one, if you didn't ask. But it will come out of this lemma. So what we assume is that G is unimodular. But nothing about H and L. Maybe one of them isn't, doesn't matter. Then, I will not write it here because otherwise some people don't see it. I will write it here, sorry. I can look at the H measure on G, left, right, doesn't matter because I assume it's the same thing, right? Restricted to H times L. And in H times L I have a unique coordinate system. Namely, the way to write it as a product of H with L. And using this coordinate system, the H measure on G is equal to the product of the H measure on H and the H measure on L, but I need to tell you which ones. So it's for the left group, it's the left H measure, and for the right group, it's the right H measure. And that's a completely trivial lemma. And the way to prove it is to use the following map, phi from H cross L to G. It's a parameterization map of this positive subset that I want to use. So H, L goes to, now I'm cheating a bit, I use a slightly different parameterization that you may have guessed. I use the parameterization HL inverse. And now I take the H measure on this positive subset and pull it back to H cross L, which I can because it's bijective by assumption, so it's not difficult to pull it back in the nice category. And what I get is a measure that's left invariant and nice. But I know what the left H measure is on the product of two groups. It's the product of the two H measures, of the two left H measures. And this L inverse makes the left H measure on L into the right H measure on L, and that's the proof. So everything is very nice, and you get this product structure. Yes?
If you don't take the L minus 1, do you get a similar lemma for NH
Well,
left
then you need to study measures that are weird, right? They are for H, on the H part they are left invariant, on the L part they are right invariant. And it's clear what measure that should be. It should be the product measure of the left arm measure and the right arm measure. So it's just to fix it to one side.
You need the L inverse to have it to be equivariant for the H times L actually in those groups.
Also, yes, yes, thank you. Right, it would be messed up also in another way. You didn't so see it. If you multiply things here on the left, yeah, but it all works out nicely this way, it also works out the other way, it doesn't matter. But here it's very nice because when you multiply this group element on the left, then you multiply this on the left, this on the left. Which means you multiply this expression here with some element here on the left and with some element on the right. And since you're invariant on the left and right, it doesn't matter if you apply to a set. And that makes it very nice. If you don't do the L inverse, it's a bit messy, right? You have to multiply here on the left and here on the right to have the same problem. It's annoying, but this fixes it nicely in the product structure. And which tells us which measure we want to use here. For GA minus it doesn't matter, but if we are going to use this lemma in that order, GA minus and then PA plus, then it will be the right H measure of PA plus that we should be using. So far it didn't matter. So far it didn't matter at all which measure we were using on PA plus. It could have been, I don't know, some weird measure with support precisely on the set that we were using. We didn't use any properties of that measure yet, except that we restricted it to the certain set. So I want to use the right H measure on PA plus. Yeah, this is looking weird. I want to simplify it now, get rid of some of the A's. I mean, this A is very easy to get rid of, right? Just cancelled. And let me save myself by looking into the notes how I want to set it up really. So let's think about this for a little while. I know that the product measure of the G minus H measure and the P plus right H measure is precisely the H measure of G. Because I assume G has a lattice, and whenever it has a lattice it's unimodular. But if it's simple, it's definitely unimodular from the beginning. And then I could take this complicated set again, a to the minus n, bn, b1, a to the n, a to the minus n, b, a to the n. Right, I could make it that complicated looking, or I can erase this in the middle, or I can erase all of that because it's a unimodular group now. So I have one normalization here that is being used. It's one constant independent of n that I divide by after I've modified my normalization here. So this depends on n, this depends on n, but the product does not depend on n. And I want to introduce now a new point, namely this point here. I call it Zn. I get f of Zn. And then I get points u, v, a to the n, right? That's what I have here. And I also want to use the, also here I want to use the product structure that I've proven. So I want to combine this into one integral, dmg, a to the minus n, u, v, a to the n. So I'm integrated over this conjugated set. And I can kill one of the integration by using this product structure. And I get here a to the minus n, b1, v, a to the n. Okay? And that's at 1. So I use the product structure both in the normalization parameter here and in the integral. That's all I do. And introduce some new point in the picture. I want to write this now as an inner product of the function f, where I integrate over y, and a set, and a characteristic function of a set. And I will match my characteristic function of the set here with what I see here in the integration. So I want to integrate over Zn u v a to the Zn b1 v, right? Because the u is in b1 and the v is in v. So when I'm integrating here, I'm integrating, there's some base point and then I have these two directions and the parameter a. And in some sense I could, now that everything is unimodular, I really shouldn't have it look so complicated. All I'm integrating it over is this u and v somehow in these two directions. And my normalization is already simplified anyway. It doesn't depend on n, so the integral also should be looking nicer.
Change the argument of f as well.
The argument doesn't change because I always use the parameter u in v1 and v in v. So it's fine. And here I wanted y to be of that form, right? That's what this here means. That I want whatever that is should be precisely of that form. So I normalize the H measure on X so that it's volume 1. I use this as a normalization for the H measure on G, so that I have this formula. So in principle you might complain that there should be a constant here, but let's just say this constant is 1.
Of y, right?
And the integration is here of y, and the integration is over y. Now, this is an inner product, right? Of the function f with the normalized 1mg b1b characteristic function Zn b1b, and this a to the n I could also write here. I mean, this is just an action applied to the set, or I could apply the inverse of that transformation to the base point, and it's the same characteristic function. So that characteristic function is equal to that characteristic function. That inner product, that I can now write as an inner product. Okay? And at the beginning, this was my average over the large piece of the horosphere, or horocycle if you do it for S sub 2. And now it's this inner product, where here I see the unitary operator for the geodesic flow being applied n times to one of the two functions that I'm taking the integral, that I'm taking the inner product of. Except that you should complain here, because it's not quite true. The n appears a second time here. But I will talk about that, but let's just ignore that. That here we have an n. Then we would have precisely the statement kicking in from in the morning, namely that we have mixing behavior. This converges to the product of the integrals. So it converges to the product of f dmx with the integral of that thing, but the normalization here is precisely such that the integral of that here is equal to 1, so multiply by 1, done. So we have to argue why this n here doesn't matter. Well, if you can show that every subsequence of that sequence has a subsequence that converges to that, then that sequence converges to that sequence. Right? That's the property of convergence. Except for the almost everywhere convergence, which doesn't have this one. Never mind. So suppose we have gone to a subsequence, and now choose a subsequence of the subsequence so that the Zn converges to Z. Because X is compact. Zn lies in X. Zn X is compact, so that this is a subsequence. So let's just say without loss of generality, Zn converges to Z. Then let's think about what this means. We have, let's draw a space. We have the set B1V applied to a point Zn. So it's some box around the point Zn in the center set. And now we vary the center and we let the center approach some limit center point. But of course the box that we are using is completely up to our choosing, so we can make it a very nice box with boundaries having null sets, etc. Which means that we have almost everywhere convergence of the characteristic function here to the characteristic function with the limit center point. So this function converges to that function, but if it converges in that sense almost everywhere, then it converges in L2 by dominated convergence. And since this is an inner product, and everything is unitary, up to another epsilon, we get that statement, of course. Okay? It was the second time I used compactness. Where was that? Where?
Not really, did you?
Not really?
No, the system of subsequences converges.
Yeah, but
No, in this step, from here to here, when you, it somehow is odd if the set B1b would be very big, then it could be that the set is somehow wrapping around and producing multiplicities. And then this expression and that expression wouldn't be the same.
But how could it wrap around if you started with a box that doesn't wrap around and you put
Yes,
it with
if you start with a box that doesn't wrap around, but what's the point? Where's the point that you start with a set n which depends on n. So you need to have a uniform. The set n is not allowed to be high up in the cusp because then it will wrap around. And then this expression, which counts the value y always only once, would be different from this expression where a value y would possibly be counted many times because the integral might wrap around. Slightly confusing, but let's just say it's good that we have compactness, and then this step is less confusing because we can make sure that the set B1 is very small by making 1 smaller if necessary, and the set V is very small by making V smaller, which we did all along anyway. So if there's no wrapping happening because this is very small and the set n lives in some compact set, then this step is also quite fine. And I think that was the only place where I semi-cheated.
Wasn't this a mistake in this estimate model?
Pardon?
Wasn't this precisely a mistake in this estimate?
Yeah. There's some issue with a certain paper precisely about such a point, yes. Okay, so we have proven the compact case. Power cycle, arbitrary G as long as we have a mixing action. Are there any questions? So let's prove Dani's theorem. Dani's theorem says if we have a non-compact quotient, the quotient by SL2 Z, then there are only two types of measures. Mu is the H measure, or mu is a periodic orbit measure. That's what we want to prove now. And we will use the same argument, but this time we will use the geodesic flow and leave the hyperbolic picture. The argument also generalizes to higher dimensions, but it needs another ingredient, which is called non-divergence. And I may or may not have time to talk about that, but let's just prove that for the power cycle flow on the modular surface. Let mu be an U invariant and ergodic probability measure. We want to identify what it is. What do we know about the ergodic invariant probability measures? Not much, other than the point was ergodic field. So we, in the context of yesterday, we can say that for every measurable function, L1 function, we have the property that the ergodic averages converges almost everywhere to the right thing, namely the integral. But now we are actually interested in continuous functions, which makes it easier, but I want to have the statement for all continuous functions at once, which is quite easy because the space of continuous functions is separable, so you just choose a dense subset, use the ergodic theorem for each one of these elements, and then do an approximation argument to say that for mu almost every x, we have 1 over t integral 0 to t f of x us ds converging to integral f d mu. And for all f in c of x, where the point of this excursion was that once I've chosen the point from the almost everywhere set, I have this property actually for almost every f, for every f in c of x. And such a point is called a generic point. So mu almost every point is generic. That's a corollary. The definition of generic is precisely that. And the statement that I've proven is a corollary of the pointwise ergodic theorem plus the separability of the space of continuous functions. And the space of continuous functions is not separable because it's not even a Banach space, because x is not compact. So I should have said CC or C0 or something, then everything makes sense. Okay? Now I want to use for this point the argument before. Now use the same argument. If possible. When is it possible to use the same argument? We needed the compactness. There's definitely true that we need the compactness. But maybe for certain points the argument can still go through. We need points that don't just go out to infinity under the geodesic flow. We sort of play four-cycling and geodesic at the same time, so I probably should always emphasize which one I'm currently using. This is the pointwise ergodic theorem corollary thereof for the homocyclic action. The argument that we just used talked about these averages, but then used the geodesic flow to discuss them and used the mixing property of the geodesic flow to produce a statement like that with a known measure here. When can we apply this argument? Precisely when there exists infinitely many n's with Zn equals, what was our definition? Was there minus or not a minus? X e to the n, or x e to the minus n. X e to the n. Minus, thank you, that should be the right. Because the correct action on the right is with a minus. So, if there are infinitely many points that live in a fixed compact set, then nothing changes from the previous argument. If, however, this sequence goes to infinity, then we can't apply the previous argument. What does the previous argument tell us if we have this property for infinitely many n's? It tells us that this average is close two along the sequence converging to integral f d mx. If possible, right? If we have this case that we have infinite many n's which lie in a particular compact subset, then along this subset sequence of averaging, along a certain subsequence of this averaging procedure, we will have this convergence. But if some subsequence converges to this and the whole sequence converges to that, well, then mu is m of x. Because this is true for all continuous functions of compact support. So the other case is where the Zn converges to infinity. Into the cusp. It goes into the cusp without return. Now let's draw the picture. We have, maybe it takes some while, right? Maybe the first 20 billion iterations we actually go up and down, up and down, and up and down, but then at some point we just go up and don't come back. So let's ignore the initial period and think about a point and a vector that never comes back. That's not it, because it's coming back under the geodesic flow. The only way the point and vector is not coming back is when at that time we point straight into the cusp. What is true for that point? Well, it's periodic under the horocycle. And if Zn is periodic under the horocycle, then x is periodic under the horocycle, but with a different period. And then the x would be one of these points far out, maybe far out from the fundamental domain, would maybe correspond to a big horocycle orbit. And that's the proof of Dani's field. It's viewed this way, somehow using the mixing argument, it's not that much more than the previous argument. But it took some time to realize that this argument is right and the easiest way to prove these two theorems.
Could you repeat what you do after you know that you are periodic under the horocycle flow?
Then I know that my x is periodic under the horocycle flow, so I know what the measure is. Right? If the x is determining the measure under this formula. If I know that the x is periodic, then this measure is the periodic orbit measure. Thank you for pointing it out, but yeah. Now we have either we can use the whole technique along some subsequence, and along the subsequence realize that these two limits are the same, and hence the measure is the Hahn measure. Or we can't apply the old argument, and then we point into the cusp at some point. Hence we are pointing north, hence we are periodic under the horocycle. And hence the original thing was also periodic under the horocycle. Any questions? Good question. Another question. So let me tell you how to prove Sarnak's theorem. And this way you get...
So how would you go about proving such a thing, but not for SL2Z, but for other gamma in SL2L?
Not SL2Z.
Yeah, because here you...
Other gammas.
You know the
Every
fundamental
cusp
domain.
looks like this.
No.
Every cusp looks like this.
No, but...
You have to...
But what you're saying is that you have the same classification for all divergent points divergent under the geodesic
Yes.
flow.
Yes. But there might be different cusps, right? There might be three such ends, and you don't know in which of these three you run into at the end. So there would be three one-parameter families of periodic orbits.
But here the cusp is such that you know that US corresponds to a periodic orbit.
It always is like that. Cusps look like that, period.
Okay.
I mean, you have to classify, you have to find fundamental domains that look very nice, and after you've done that,
But
you will see that they all look like that and they have the same behavior.
But it's special to SL2R, right? In general rank 1 groups you can...
Yes. So the argument needs a completely different refashioning, a completely different new input that you don't see for SL2R, because orbits that diverge go to infinity, you can classify completely for the quotients of SL2R. And it sort of links perfectly to rational properties. Meaning, you only go into the cusp and never come back if you point straight into the cusp. And this is somehow a very low-dimensional phenomenon that is completely understood. And there are no fractal dimensions and so on. But if you go to SL3R and you look at a particular geodesic element, diagonal element, you can ask what's the dimension of all the orbits that go to infinity and never come back. And if you use the correct element, then the answer is the whole space is 8-dimensional and you need to subtract 2/3. So it's 8 minus 2/3. That's the dimension of the space of all orbits that go to infinity in SL3R for a particular one-parameter flow. So it means it's not a rational property, it's a weird property, and it will not help you to classify invariant measures for the horospherical orbits. So you need to do something else, and this something else is called non-divergence. For the horocycle flow, for the horospherical action. So this is an additional ingredient. You can do the same argument, but it's a bit more work. Let me not do that. It will be in the notes at some point. But what I want to do in the last 5 minutes that I have from the beginning is to prove Sarnax theorem, which I've only just erased. So let me draw it again. This is our fundamental domain, and here we have an orbit, and it's actually an orbit of a horosphere, of a horocyclic flow, and I have a parameter y, which is the y coordinate of that orbit. And I have a function f, which is a function of continuous compact support on the space, which is SL2Z quotient by SL2R, or I could also say PSL2Z quotient from T1H, right? Same thing. Now, what are continuous functions on a quotient? Continuous functions on a quotient are continuous functions on T1H that happen to be invariant under the action here. So I can think of as a function, compact support on this quotient, I can think of as a function defined on the whole upper half plane, together with a vector. So upper half plane cross direction, which is T1H. And then I can integrate from minus 1/2 to 1/2 f of this thing. I take f of x plus I y, comma I. I need to have a direction also because my function depends both on space and direction. And the direction I'm using is I, pointing north. Maybe I should normalize it by the length what it has. I have this function and then I'm integrating over x and leave y fixed in the integration. I have a one-dimensional integral which corresponds to integrating over horocycle orbit corresponding to this periodic orbit. The claim is that this converges to the integral of f dmx, which is a three-dimensional integral over all of x, as y goes to 0. And the proof is homework. Why is it easy? Because you use the same argument. You take a reference orbit, the orbit of length 1. Take this reference orbit. It's actually easier than both of the theorems before. because in both of the theorems before we had to use varying points, and then we had to use the mixing statement for varying sequence of functions that only varied in a mild way, and that's why we were able to do it. Here we use a thickening of this one periodic orbit in the other direction as before, that is fixed. We use this fixed thickening of the fixed set and then pull it back and get a small neighborhood of this guy. We expand the direction that we're interested in and make it very long. We contract one of the other two directions, make it thinner, and the geodesic direction we keep in the same length. And then it's really just the mixing statement, this statement, after this thickening. And then there's another theorem, which I just want to quickly state because it's a wonderful theorem, but I will not prove it. We will generalize it tomorrow and again not prove it. This is Danny Smiley. Let x be SL to Z, quotient by SL to R, or some other non-convex quotient. Let x be in X. Then X is generic for an ergodic measure. That's unexpectedly wonderful somehow. I mean, usually you don't have such statements. Other than in the uniquely ergodic case. If you're uniquely ergodic, then every point is generic for this one and only measure. But we already established that it's not uniquely ergodic. But still you have the same statement, same type of statement. Every point is a generic for one ergodic measure. Which? Well, it depends on the point. The point could be periodic. Then it's clear what is going on. And if it's not periodic, the statement goes further and says it's actually generic for the Haar measure.
But didn't we see it? Because if it has
We
divergence...
saw it along subsequences. So yes, we already have proven that along some subsequences, but that is not really the definition of generic. Right? Generic says it should hold no subsequences necessary. So you have to improve the statement from it's true for a subsequence to it's true. And the argument doesn't do it.
We know if the geodesic flow is bounded, then...
Yes, we know it for points that don't ever venture into the cusp. Those are a null set of points because of ergodicity of the geodesic flow. And for all other points that are not periodic, we know it along a subsequence. And to prove this, it suffices to use the non-divergence for the horocycle flow again,
So
which is much easier to prove.
This ergodic measure depends on the point.
Yes. So, and the statement is, if X is periodic, well, then you know what's the measure going to be. And if it's not periodic, it's the Haar measure that it's generic for. So it's this, which is clear that it should be because along a subsequence we already know it. Yes. Okay, thank you. Any quick question? For sure we have those on the beach.